Okay. You guys there?
Whoa,
I'm here.
Yes.
Ah,
We're here.
I'm here.
Let's get some light on this subject.
Yeah, how you doing tonight? Yeah, I gotta open up a notepad window here so you could
Yeah, there you
see
go.
my face. There we go.
Lighting by notepad.
Yeah, how you guys doing tonight?
All right.
We're doing good.
We have lovely weather up here at
Yes.
Chabot.
Yeah.
Slight breeze, yeah.
We have no excuses. There's
Well, wait
there's
a minute.
always an excuse.
We have our fingers crossed too.
we do have our fingers crossed on all the technical matters, but
Yeah,
we tried to
are-
work them up and work them out in advance. So.
We are using computers, so everything
Yeah,
is
anything.
Good,
Well,
Anything's possible. Yeah.
I'm Rich Ozer. We are here with Gerald McKeegan and Rick Taft, and it's virtual telescope at the Chabot Space and Science Center. And I want to remind everyone that the Chabot Space and Science Center is still closed, although we are gearing up to open in November. In the meantime, we depend on donations from people like you and others and our sponsors like Fremont Bank to keep our programs going and to help us reopen with all the resources that we'll need to provide a new experience, and
Yes.
that will be also in association with NASA, because the Chabot Space and Science Center is now going to be an official NASA Visitor Center, and we have a partnership with NASA Ames and some new exhibits going in right now that are related to that partnership. So it should be interesting, should be fun, and I hope you'll all come up and join us live in person when we reopen in November. Anyhow, we're here with the 36-inch Research Reflecting Telescope, otherwise known as Nellie. And but before we do live viewing tonight, I think we have a special presentation. Is that right, Gerald?
Yes, we do. I'm just keep talking. I'm just getting it set up. Yeah.
Oh, what am I going to say?
Well,
you might mention about donations and so on, and
yes,
go into
that's
the
true.
Facebook page.
That's true. For you folks who are on Facebook, there is a donation button. And for those of you on YouTube, if you visit our website at chabotspace.org, there are instructions on making donations and also learning how to become a member of the Chabot Space and Science Center, which is a great way to support us. So you can consider those options if you want to contribute to Chabot.
All right, I am ready.
Oh, good.
All right.
All right. Why don't you tell us what you got?
Okay, so once a month we do a presentation called The Sky Tonight, and it's a video that's produced by Don Saito. Don is one of our volunteers up here at Chabot Space and Science Center. Don has been with Chabot for, I think it's 23 years now. So he's been around for a long time, and he produces these nice videos showing you a little bit about the different constellations that you would see in the night sky. So without further ado, I'm going to share my screen, make sure to turn on the sound, and fire away. Here we go.
Greetings, stargazers. Just 3 more months to go before we'll be able to meet in person inside our amazing Zeiss Planetarium at the Chabot Space and Science Center, situation depending. While these online planetarium shows are okay, there's nothing like the simulated real thing, which in most cases is better than the actual real thing. Until Chabot's reopening in November, we can still use nature's planetarium, also known as the real sky, to step outside, tilt our heads back, and see at least some of the amazing things I'll be pointing out for you tonight. I'm of course talking about the constellations. There are people, animals, and objects up in the night sky. They've been there for millennia, but most people are unaware of them as they glide by unnoticed right over our heads every clear night. Tonight, let us explore these objects and characters and let them become our friends and familiars, just as the ancients did. To start, let's consider the reason we don't see all the constellations at once. The Earth has 4 seasons: spring, summer, fall, and winter. Well, the constellations also have seasons, having to do with the Earth's yearly orbital path around the Sun. I want you to think about that for a moment. The constellations have seasons too. Just realizing this fully can help make knowing the constellations easier. We can only see stars by looking away from the Sun at night, which changes our view of the stars as the Earth makes its orbit around the Sun throughout the year. At this time, we are beginning to transition from the summer stars to the fall stars. Unfortunately, unless you're at a good dark sky site, and if the moon isn't too bright, most constellations will be somewhat hard to see fully. But most constellations have at least a few bright stars to help identify them, and the better your viewing location, the more you'll be able to see. When we were in the middle of the summer season, we only had about 7 hours of night, as opposed to the nearly 10 hours of night during the winter. But as the Earth slides along its path around the Sun, the number of nighttime hours is now slowly increasing. We astronomers like it when we have more time to view the constellations. A good first step to finding the constellations is done by knowing your compass directions. Since around March or April, we were using the Big Dipper to help find the North Star. But as just mentioned, the constellations have seasons, and this month is the end of Ursa Major's season. The Big Dipper is part of Ursa Major. But not to worry. As it just so happens, when one pole-finding star grouping sets, another rises. Cassiopeia the Queen, also known as the Big W. As you can see, Cassiopeia has just risen in the north-northeast. Its 5 brightest stars make up its iconic W shape, but there are a few more fainter stars I'll point out to make its actual shape more apparent and to show how we can use it to find the North Star. The constellation of Cassiopeia is actually her throne. It's upside down in the early evening, but this star here makes up the throne's seat. Off the tip of the more squashed end of the W shape is this star here. If you draw an imaginary line from the tip of the W and that star, it points directly at Polaris, the North Star. Now, Polaris is the only star in the entire sky that stays pretty much right where it is. So no matter what time of night it is, or even what month of the year it is, all you need to do is face it, and you'll always be facing due north, with east directly to your right, west directly to your left, and south directly behind you. All the other stars wheel around this pivot point anti-clockwise, making them appear to rise in the east and set in the west. This is of course an illusion caused by the Earth's rotation, which gives the appearance that the stars are moving, when in fact it is the Earth that's spinning. If you think of the Earth as a spinning top, and you extend Earth's north polar axis straight up into the sky, it points almost directly at Polaris. Using Polaris, we found all the compass directions, but Polaris is also the end of the Little Dipper's handle, whose official name is Ursa Minor, the Little Bear, a small constellation. It's a bit faint, but from Polaris, you might be able to trace its curving handle to its bowl. The 2 brightest stars at the end of its bowl are called the Guardians, because they seem to march around the North Star like protective sentries throughout the night. Arcing up and over the Little Dipper, we find the tail of Draco the Dragon. He's got feet, a short belly, a long neck, and squarish head. There be dragons up there. I'll bet you didn't know that, but now you do. Going back to Cassiopeia's W shape, the non-squashed end of the W points directly into the face of her husband, Cepheus, the king. He's upside down at this time, but he's got a triangular crown, a face in profile, a stylish pigtail, and he's smiling, 'cause he's the king. At this juncture, let us turn around and face the southern horizon. This will allow us to see the rest of the night's constellations more easily, like so. Arcing above the southern horizon is a kind of invisible line where all the zodiacal constellations can be found. This line is called the ecliptic, and is also where the sun, moon, and planets move along. This is why the zodiacal constellations were so significant to astrologers. Not that astronomy scientists believe in the pseudoscience of astrology, most don't. But astrologers were some of history's first astronomers, and for their early work, we are in their debt. Starting in the east and moving to the west, we have the constellations Aquarius, the water bearer, Capricornus the goat, who currently contains 2 planets, Jupiter and Saturn. Then we have Sagittarius the archer with his bow, Scorpius the scorpion with his bright reddish heart Antares, and Lyra the scales. We'll only talk about the goat, the archer, and the scorpion tonight, as they are the only ones bright enough and high enough to actually be seen. Starting just above the southeast horizon, we find Capricornus the goat, with his horn, head, body, legs, and tail. Below his body, we'll find everyone's favorite ring planet, Saturn. If you get a chance to look at it through a telescope, do it. It's quite amazing. Pictures on the computer or in a book are fine, but seeing it with your own eyes through a telescope is a different, sometimes inspirational experience. Also near the goat this month is the planet Jupiter, located just off his horn. Jupiter is the largest planet in our solar system and always worth a telescopic look, especially since it's so close to Saturn. To the right of the goat, we find Sagittarius the archer. He's a bit faint with his triangular head, quadrilateral chest, and large lower body with legs and feet. His right arm is holding out a bow, while his left arm is held high above and next to his head, as though he just shot an arrow. Sagittarius contains within him an asterism, which is a bit easier to see. It's called the teapot, seen here. Look for the teapot if conditions prevent you from seeing the archer in its entirety. To the right of the archer, we find a fairly easy to see constellation just above the southern horizon, Scorpius the Scorpion, known by astrologers as Scorpio. He has 2 claws, a long body, and a stinger at its furthest extremity. He also sports a bright reddish heart located in the upper third of his body called Antares. Antares is so named because it's reddish and found close to the ecliptic, just like the planet Mars. Remember, all the planets move only along the ecliptic, and sometimes it brings Mars and Antares into close proximity to each other. To those familiar with Greek mythology will recall that Ares is the Greek god of war, and the planet Mars was thought to represent Ares. To avoid confusing the 2 reddish stars with each other, they called one Ares, aka Mars, and the other one Ant-Ares, or not Mars. Those clever Greeks. Leaving the ecliptic, we come to 3 relatively easy-to-see constellations: Lyra the Lyre, Cygnus the Swan, and Aquila the Eagle. Each of these constellations is tied together by an easily seen asterism, one of those familiar star groupings that aren't constellations I mentioned earlier with the teapot in Sagittarius. Each of these 3 constellations contains one very bright star, which together form the Summer Triangle, so named because it only begins to be seen in the early evening at the start of summer in June. Let's check out these constellations right now. First up is the constellation Lyra the Lyre, which is a small Greek harp, and not someone who tells untruths. It contains one of the brightest stars in the sky, Vega, first of the stars that make up the Summer Triangle. To the left of Lyra, we find the majestic constellation Cygnus the Swan, with his broad sweeping wings, long neck and nose, and his bright tail star, Deneb, the second star of the Summer Triangle. Below both Lyra and Cygnus is the constellation Aquila the Eagle, with his bright eye Altair, which is the third and final Summer Triangle star. The Summer Triangle is very easy to see, even in fairly light-polluted skies. It's also a kind of unofficial direction pointer, as it points almost directly due south. To the right or west of Lyra is the constellation Hercules the Strongman. His rectangle-shaped head is the asterism known as the keystone, and while Hercules is somewhat faint, the keystone is the easiest part of him to pick out. Conditions permitting, from there, you can figure out the rest of him: his outstretched hand, his other arm holding a big club, his body, and 2 running legs. And that's it. There are other smaller or fainter constellations out there which I encourage you to look for using a good book and maybe a pair of binoculars too. Speaking of good books, I cannot more highly recommend the book The Stars, A New Way to See Them by the author H.A. Rey, who you may know as the same author who wrote the Curious George books. Rey was a scientist who wasn't satisfied with the way modern star charts were drawn. The astroscientists were not interested in the characters, objects, or stories behind the constellations, so for convenience, they just connected the brighter stars into weird geometric shapes, slapped on their Greek names, many of which would mean nothing to the common person, and left it at that. That's all fine and well for them, but for us regular folk, we're more interested in the fun stuff. If you really want to learn the constellations, get Ray's book, which can be purchased from Amazon.com for about $18. I'd also recommend getting a pair of binoculars before getting a telescope. Binoculars are cheaper and easier to use, and there are many wonderful deep sky objects that can actually be best seen with just a pair of binoculars that are noted in Ray's book. If you do want to get a telescope, ask us or research on the web how to make an informed purchase. Be warned, there are a lot of bad telescopes out there with cheap components and shaky, muddy, fuzzy views that will disappoint you every time. A good scope will inspire you and your children to a lifetime of deep space exploration and an appreciation of science and nature in general. If you're interested in getting into the hobby of astronomy, joining a local astronomy club can be most helpful. Chabot is partnered with the EAS, the East Bay Astronomical Society, which has many activities and resources you'll find essential to help you get started in this amazing and beautiful study of our natural universe. Thanks for watching this video. If you like this content, be sure to click the thumbs up button, subscribe to our channel, and hit the bell notification icon to find out when new content has been uploaded. This will really help our channel to grow, which would make us all very happy. And until we meet again, we'll see you in the future!
All right.
I never get tired of that.
No. No, Dawn really weaves a really nice tale of the night sky. I never get tired of listening to that.
Yeah. You know, he shows a technique for finding the North Star, and there are actually several different techniques to use. You know, most of the time, or not most of the time, but at least half the year, the Big Dipper is in the night sky, and you can use the Big Dipper to find the North Star. But when the Big Dipper is too low, then you have to come up with other techniques. He likes to use a technique involving the constellation Cassiopeia,
Yep.
and a faint star off the flattened end of the W. I use a couple of stars in the constellation Cepheus. So different people have different ways of doing it. But, you know, the idea is find the North Star and go from there.
Yeah, certain telescopes that you buy, it's really important to know how to find the North Star, because you have to actually align them out on the North Star, or else you cannot track what you're looking at for more than, 20, 30 seconds. So it's it's kind of an important star to be able to find. And I like
it is, and it's actually pretty easy to find too. So when I'm aligning the telescope out in the backyard, I'll use my cell phone, and that gets me, I'll use the compass, I have it set for true, and that gets me pretty darn close, and then I can make some fine-tune adjustments. So, you have a couple of stars, you got the pointers and the Big Dipper, I have my iPhone, it works for me.
That's a pretty good way to do it. I hadn't thought about that. All right. I think it's a good night for doing gas giants.
Yeah. So what would you like to start with? How about Saturn or Jupiter first?
Well, why don't we do Saturn first? And although both have crept out beyond the
we can do either one.
The other dome. So, but why don't we work from kind of west to east? And
all right, stand by here. I'm going to do a little hop to a star near Saturn. We'll sync on that and then go to Saturn. So we're using our 36-inch reflecting telescope, the one we call Nellie. Nellie is a computer-controlled telescope. So all we have to do is tell it where to go, and it kind of does all the work for us. Rick, if we can get into live view and actually share it on the screen.
We're in.
We're not sharing.
We're not sharing. Okay. Well, about technical difficulties. Let me stop sharing.
So anyway, when we make big moves with the telescopes, sometimes what we have to do is kind of do an intermediate stop and make sure everything is synchronized just right so that the pointing is very accurate. So you're in live view, right?
I should be in live view. Yep. Yep. There it is.
Yeah. Okay. You must be using a relatively slow shutter speed.
Well, it's a 2-second shutter.
Oh, well, that's why it's taking so long. Okay. There you go. Yep.
So Alan asked a good question. He wanted to know how do you polar align when you're in the southern hemisphere, and it's a little more difficult. You have to use the southern. You have to use the Southern Cross, but and then you either have to do what's called a drift alignment, or have a southern polar scope that will help you find the south celestial pole. But you basically use the Southern Cross as your guide.
So Rick, you're going to have to slow your shutter speed way down here if we're going to see Saturn. We can see all its moons. We see Titan off down on the right.
Oh yeah,
there we go.
There we go. Yeah, it looked like an elliptical galaxy there for a second.
Yeah.
Okay, so we slow it down. Unfortunately, we lose the moons.
Yeah, I know.
That's all right. That's okay.
All right, so let's zoom in a little bit.
Yeah.
There we go. Very nice.
Oh, not too bad. Not too bad at all. So this is Saturn and its rings. And there's Rick messing with the old...
Yeah, Gerald and I were telling jokes at your expense the other night.
Yeah,
you told me to do this, Go. You know,
we're going to delete that.
Yeah, we showed you once, and then you went to town.
Okay, let me back out. No more high definition for you guys. You know.
No more high definition for you.
No. Okay, I control the horizontal, vertical, and so you guys better watch it.
Yeah, so as you can see, it's kind of going in and out of focus quite a bit. So that tells us that tonight is not ideal seeing conditions. And we do have a little bit of a breeze blowing up here at Chabot, so we're getting some turbulence in the air. And what that means is that the air is constantly changing density. And because of the change in density, the refraction of the light from Saturn is changing from 1 minute to the next. And that's why it seems to be going in and out of focus like that. That's pretty common. There are some techniques we can use to kind of counteract that. If we wanted to get a really good image, we'd take a whole bunch of very short exposures, pick out the best of them, stack them, and then give you a nice still image. But this is typical of what we encounter when we are viewing live with the telescope. So you see the rings, you see the planet itself. Saturn is a gas giant. Its diameter of the planet itself is about 9.5 times the diameter of the Earth. The distance across the rings from one edge to the other edge is about the same as the distance between the Earth and our moon. So roughly 250,000 miles across the rings. The rings are composed of ice particles, anywhere from the size of a fist or smaller to some of them might be as big as a small desk. And they orbit around Saturn in a very flat plane. The depth of the rings is only a few tens of meters at the most. So it's a pretty thin ring plane. And the ice particles in the ring, they orbit around the planet at different speeds. So the ice particles that are close into the planet orbit faster than those that are much farther away. And that kind of creates a shearing action within the rings that really causes the rings, although we see them as only one or two or three broad rings, when you look at it close up, you see that there's actually thousands of individual rings that kind of are one right after the other that form the larger rings that we see from here on Earth. We did have a spacecraft go to Saturn and orbit around Saturn from 2004 until 2015. And it sent back lots of really cool images of the rings and of Saturn itself and of all of Saturn's moons. I think it's got something like 74 moons now, and that could be even more than that. So there's a lot going on up there.
So Mario asked a good question on YouTube, and he said, I wonder what people thought the rings were when they were first discovered. Well, when Galileo first took notes on what he saw when he pointed his telescope at Saturn, he thought he had no idea what it was. So he just said, it looks like a planet with ears. And because he kind of had a more blurry version of what you're seeing right now.
Right.
And then after that, people didn't really know what to make of it. And there was a long period of time where it was just assumed it was a solid structure, right? And but after a while, as we understood, physics and the material science, behind bodies in the solar system, and had better telescopes, it became pretty obvious that it was particulate matter, and eventually that was proven as we sent spacecrafts out that way. So.
I've got a couple of images from the Cassini spacecraft that I can share with you if you like.
Why don't you? I think that would be a good idea.
Yeah. Hang on just a second here. I'm going to bump you off, Rick.
Okay.
All right. So
not permanently.
No. Yeah.
Okay.
Yeah.
I'll be here.
Yeah, they offered me a contract, but it wasn't nearly enough. So this is an image taken by the Cassini spacecraft, which again orbited around Saturn from 2004 to 2015. And you see the rings, and now you can see that there's actually more to the rings than what we see from Earth. In fact, this ring here, this is the E ring, I believe it is. That ring is actually barely visible from Earth. You have to have a really good telescope to see that. But you see this gap here. This is called the Cassini gap. And if you look right there, there's a moon. And that's what's causing the gap. In fact, most of these gaps that you see in the rings are caused by little moons orbiting Saturn within the rings. And there's quite a few of them. This one is called Pan, which is an odd-shaped moon. It looks like somebody sort of made like a little round ball with some clay and then took a long tube of clay and wrapped it around the middle. It's really an odd-looking moon. Ray Howard, if he's out there, he's probably mad at me now because I just gave away the answer to one of the questions in his.
I'm sorry, Gerald. That went right over my head. Would you mind repeating that?
No, I will not repeat it.
That's funny.
Pay attention. Okay, so here's an image. This is actually a Hubble Space Telescope image of Saturn, but here's another image that I wanted to show you. And here you can see even more sort of mini rings within the larger rings. But look right here. Here's another gap in the rings, and here's a little tiny moon in that gap. Now, this picture was taken at a time when the rings were edge on to the path between the sun and the planet. So you get these really long shadows. This moon is not that big, but because of the angle of the sun, it casts this really long shadow across the rings. But you also see the disruption of the adjacent ring particles by this moon. Although this moon is small, it does have a gravitational field. And what happens is the ring particles are disrupted by the gravitational field of the moon. But the ring particles closer into Saturn are orbiting faster than the ring particles farther away. And so the disruption appears in one direction, closer into Saturn, and appears in the other direction, farther away. And these patterns in many of the Cassini images, they look like little propellers. And so that was kind of the nickname that NASA scientists gave all these little features buried within the rings. They called them propellers because they had this kind of a pattern caused by little moons within the ring. So pretty cool.
So Tim Thompson pointed out that it was James Clerk Maxwell who proved that the rings of Saturn could not be solid, and that was in it was actually 1856. And he received what was called the Cambridge Adams Prize for his work on the motion of the rings of Saturn. And so at that point in time, there were three possibilities: that the rings were either rigid, that they were fluid or partly gaseous, or that they were composed of isolated masses or particles. And what he did is applied mathematics to it. And he determined that the only stable construct for Saturn's rings was the third, composed of individual isolated masses or particles. And that was then proved in 2004 when Cassini visited the rings, and we were able to get those photographs that Gerald was showing you.
Yeah.
So
many more.
Yeah, and many more. But it's a great example of how applied mathematics was used to kind of prove a hypothesis, and then the evidence collected more than 100 years later to show that he was absolutely right.
Well, shall we move on to Jupiter?
Yep.
All right.
Sounds like a plan.
So, Rick, if you want to share your screen and do the live mode again.
Yeah.
Okay.
Very good.
It doesn't look like Jupiter.
No, but the screen share
disappeared.
The screen share, yeah. And at least screen share worked. That's great.
Yeah. Oh, there's some moons.
Yeah, you're zoomed in, Rick.
Yeah, gotta zoom out a little bit. Yeah, only 486%. There we go.
There it is. All
so
right,
yeah, we can stop there. You can see all four of the Galilean moons right now.
All right, should we make this a little easier to see?
Yeah.
Yeah, there they are. So, do you know what the different moons are?
I could find that out if you get
well. So the four moons that you see one real close to on the right, and then three others on the left. The one real close on the right is most likely Io. Those are what we call the Galilean moons. They were discovered by Galileo in January of 1610 using his very small crude telescope, but he was able to see them. Now, the interesting thing about the Galilean moons is they're so bright and so easy to see that you can see them even with a pair of binoculars. So, if you want to rush outside right now, if you've got some 8X or 10X binoculars and take a look at Jupiter, you might actually be able to see them. The moons orbit fairly rapidly. In fact, Io, that one that's real close, takes just under 2 days to orbit Jupiter. So if we were to just sit here and watch this for about an hour or so, we would actually see Io change appreciably its position as it's orbiting around Jupiter. The other thing that's interesting is you notice that they're all kind of in a line. Well, it turns out that the plane of the orbit of the moon, so they're all pretty much on the same plane of orbital plane, and the plane is aligned so that it's parallel to our line of sight to Jupiter. So we're kind of seeing the plane of the orbits edge on. And as a result, the moons don't appear to us to be going around. They appear to go back and forth, crisscrossing back and forth, passing sometimes in front of the planet, sometimes behind the planet. And one of the neat things about when they pass in front of the planet is they cast shadows on the planet. And with a reasonably good quality telescope and nice clear night, you can actually see the shadow of one of the moons passing across the planet. You have to catch it right.
I do have the information on the other three. So
right.
You are correct in that Io is the one that is closest to Jupiter on the right-hand side of the image. And then if we look on the other side of Jupiter, it goes Europa, Ganymede, and then Callisto.
Yeah, I kind of guessed that the middle one was Ganymede. Ganymede is the biggest moon of Jupiter. It's also the biggest moon in our solar system. In fact, if Ganymede was orbiting around the sun instead of around a planet, it would be considered a normal-sized planet. Yeah, let's see. Which one was Europa? Was that the one closest in of the three? Yeah, okay. Mm-hmm. Yeah, so Europa is an ice world. It's about the size of our moon. It is covered with a relatively thick layer of ice, but under the ice, there is a liquid ocean. And it's obviously got some organic chemistry in that ocean because the ice is cracked in many places, and we can see kind of this brownish ooze that has oozed up through the cracks. So we've done some analysis of that brownish ooze. It contains organic compounds, but organic compounds does not necessarily mean living material. In chemistry, any kind of a compound that's composed of carbon and hydrogen and could be oxygen or phosphorus or anything like that, those are all considered organic compounds. So like methane gas is considered an organic compound. But there are some pretty complex organic compounds, and that's what that brown ooze that's coming up through the clear cracks appears to be composed of a lot of complex organic compounds. So we're very interested in Europa, and there is a mission now on the books at NASA called Europa Clipper, which is a mission to go to Europa, put a spacecraft in orbit around it, and see if we can learn a little bit more about what's underneath the ice on the surface. And who knows, we may find life there.
So Margot asked, how close is the closest moon to Jupiter, and how far out is the farthest of those moons, which we were looking at, Callisto? So Io is, here's the problem. I'm not sure if they're talking about from the center of Jupiter or
always
it's always the center.
Right.
So in that case, it's about the same as Earth to the moon. The distance from Io to Jupiter is 262,000 miles. And so it's 250,000 miles, right? So it's pretty similar to the moon, and from moon to Earth. And Callisto is a bit over 1 million miles. It's 1.1 million miles. So that's about how far the James Webb Telescope is going to be from Earth.
Yep. Now, just to put things in perspective, Rich said that Io orbits about, 260,000 miles?
262,000, yeah.
262,000 miles from Jupiter. That's actually a little bit farther than our moon that orbits around the Earth. Our moon takes depending on how you want to measure it, about 27.5 days to orbit around the Earth, make one complete orbit around the Earth. Io takes less than 2 days to orbit around Jupiter. And the reason is because Jupiter has so much more mass. It is a bigger planet physically, but it has a lot more mass than the Earth does. And it's the mass that governs the orbital velocity. Jupiter's size is 10.5 times, 11.2 times the diameter of the Earth. So it's about 88,000 miles across, and it's got a lot of mass. And it's the most massive planet out of all of the ones in our solar system. And because of that, the moons orbit very rapidly.
So another good question from one of our viewers on YouTube: what happened to the Cassini spacecraft at the end of its life? Well, they pointed it at Saturn's atmosphere, and it took a dive into the atmosphere and sent some data back up until the very last moment of its life.
Until it started breaking up. Yeah, they called it the grand finale. That was in 2015. Mm-hmm. And like Richard said, up until then, they had been orbiting around Saturn outside of the rings. But in the grand finale, they actually put the spacecraft into an orbit that would carry it between the rings and the planet. And then it eventually entered the atmosphere of Saturn and was destroyed. Right. And with it went my name.
That's right. Yeah, a lot of us had our names on the spacecraft.
Yeah, they had a little CD disc that they attached to the side of the spacecraft, and it had names of lots of different people, including all the people who worked on it. And at that time, I was working in the space industry, and we had materials on the Cassini. So.
Hey, Rick, why don't you shorten the exposure on this so we can see some surface detail, maybe?
Yeah.
Okay. I have to go more than that.
You drop that ISO down, probably.
Yeah.
And there we go.
Get and close.
There we go.
Yeah.
Now.
Do I need to center it up a little bit here?
Nah, we're okay.
No, it's okay. I can center it up here.
So what we can see are some of the cloud bands. There we go.
Yeah. So you see some dark bands and some light bands. The dark areas are called belts, and the light areas are called zones. And they, as a general description, they correspond to high and low pressure areas. The zones, the light areas, are the higher pressure areas, and the belts, the dark bands, are the low pressure areas. Now, Jupiter is a gas giant, so you're looking really at the tops of clouds. In Jupiter's atmosphere, they have the high and low pressure areas, just like they have here on Earth. On Earth, our highs and lows tend to form little swirlies within the atmosphere. But on Jupiter, because of its rapid rotation rate, it wraps the highs and lows all the way around the planet, producing these belts and zones that you see here. Jupiter's day is only 9 hours and 50 minutes long on average. And so at the equator, it's rotating at the rate of 26,000 miles an hour. That produces some pretty strong winds in the upper atmosphere of Jupiter. Hence, you see the belts and the zones, the high and low pressure areas wrapped around it.
Unfortunately, if the seeing was better tonight, we would see the great red spot right now.
Yeah.
And it would be on the lower belt, off toward the left-hand side of Jupiter.
Oh, actually, you can see it. There it is.
Yeah, but it's kind of tough for
Yeah, on
that was-
Facebook you don't see
on
it so well.
Facebook
Okay.
and other and other media. But maybe you should play with those sliders, Rick.
Oh no!
I'm telling you, this is my opportunity. Oh, look at that.
There we go. Yeah, it's starting to come out. Actually, it's working.
It's working. Well, what I was hoping to see
that
is,
only encourages him.
I know it does. I know.
I gotta have something.
We've
to
created
do
a
here,
monster here.
They told me where the the switch was, so now I'm using it. And actually, what I was hoping to see, Io, as you know, was very close to the to this edge of Jupiter, and you could actually see the shadow of the moon if I'm using some astronomy software. I was hoping to see it here, but I think we'd have to do some video imaging to be able to bring that out.
But what's your shutter rate right now?
1,000th of a second.
Oh, okay. Do me a favor, zoom it in a little bit more.
Okay.
All right, that's good.
So we can try upping the shutter.
No, just leave it alone. There we go. Look at that. Now you can see the red spot real well.
Oh, there you go. Somebody's been adjusting the focus.
Yeah, I was tweaking the focus. That's why.
Yeah, that's great. Great.
So you can clearly see the red spot now. You might point that out, Rick. Right there.
Look for the red cursor right there. Yeah.
The great red cursor.
The great red cursor for the red spot.
So this is a good view. Yeah.
Good job.
Now it was the right thing to do, wasn't it? To use the HD, the high definition.
Yeah.
All right, wasn't that okay? Come on.
Occasionally, it might be a good idea.
Boy, it's hard to. This is a tough audience, I'll tell you. Anyway, no, it's actually
no. The audience is fine. It's your colleagues that are a problem.
Yeah.
I should say my immediate audience right here.
Yeah. Rick, if we couldn't give you a hard time, we couldn't give you any time at all.
I know. I should feel honored there.
Yeah, there you go. Yeah, now it's fading out here. So,
all right.
Well, let's see if we can look at a few other objects. We're kind of close to.
We're kind of on a roll. Well, we could do that. You want to do that, or do you want to?
Or
let's go.
Let's do M2 first, and then that other target that you're talking about.
All right.
Because it's a little on the low side.
All right. Let's do M2.
All right. So I'm gonna. You want to zoom back out, Rick?
Well, if you guys are really good, you could use the high zoom and still find what you're looking at. Just saying.
Yeah, there's that. All right, hang on here.
Yeah, let's move before my camera sensor blows up.
Yeah. All right, we are there.
We're okay.
You're there. I see a star, but we ought to be able to see a lot more than that. So you might need to go like 10 seconds or 20 seconds or something like that.
Let me just snap this is 1 second. Oh, you're looking at a cluster. Okay, let's go. All right, here's 10 seconds. What cluster is this, Gerald?
This is M2.
Oh,
it's a globular star cluster. It's about 39,000 light years away. Is it actually taking a picture? Oh, there it is.
Yeah, there it is.
Yes, actually, it's way overexposed.
Yeah, let me adjust the position a little bit. So M2 is another one of those what we call core collapse globular star clusters. It has a very dense core. Globular star clusters are balls of stars out in space, typically having several 100,000 stars up to 1 million stars. And the stars in a cluster are orbiting around the center of the cluster. You might want to get rid of that. Yeah.
Take the HD off for now.
Yeah, because you're getting kind of bloated there.
Yeah, I was wondering what was going on here. In fact,
now in the universe of globular clusters here, we are always talking about the different hypotheses of how they're formed and where they came from, and the vast majority of the ones that we see and have observed in the Milky Way pretty much accept the fact that they were formed in the Milky Way galaxy, and they were formed by the condensation of hydrogen gas into stars, but very large clouds of hydrogen gas, so that very large clusters of stars were formed at roughly the same time.
Right.
But M2 is a little bit interesting because it's part of something known as and you're not going to believe they called it this, the Gaia Sausage, which is the hypothesized, yeah, believe it or not, the Gaia Sausage. Sounds like you can get a breakfast burrito, made out of the Gaia Sausage. The hypothesized remains of a merged dwarf galaxy. And so it's not entirely certain that it was originally a Milky Way object. It could have been part of this dwarf galaxy. It could have been coincidental. It could have been the collision of a dwarf galaxy in the vicinity of M2. And it's a bit of a mystery. We may never really know the answer. And it's 175 light years in diameter, which I think is an interesting.
Yeah, and close to over 500,000 stars in it. So just to put that into perspective, the nearest star to our sun is about 4 light years away. So if you were to space out 4 light years, stars at a spacing of 4 light years over, say, 160 light years, you'd get about 40 stars spaced out across 160 light years. Here you've got thousands of stars in that same spacing. So these stars are really close together. They sometimes bump into each other. Sometimes they pass so close to each other that one star with stronger gravity will pull the outer layers off the other star. That goes on all the time. And one of the interesting things is if you lived on a planet orbiting around one of these stars, you wouldn't have a nighttime because there would be so many stars so close to you most of the time that you just wouldn't, they'd all light up your night sky and you wouldn't have a dark sky. Now, the stars that are orbiting around the center of the cluster, but they all aren't orbiting in nice circles. They're actually orbiting in highly elongated ellipses. So the stars go in close to the center. When they're close to the center, they're moving very fast. They orbit around the center, and then they swing out, and they swing out pretty far out from the center. And as they go out, they slow down, and eventually they reach their maximum distance, and that's when they're moving the slowest. And then they basically drop back in towards the center, and as they drop back in, they speed up and rinse and repeat. And all right.
Very cool. Nice image.
Okay. Well, shall we move on to
our third gas giant of the night?
Yeah.
So we're going to look at Neptune.
Yeah, it's a little low off to the east, but we'll take a look and see how it looks here.
We should at least be able to see its color.
I'm hoping we can see it.
All right, let's see what happens.
Yeah, okay, I see it. All right. I was worried that we might be blocked by the dome.
No.
So Neptune is the 4th largest planet by diameter. It's slightly smaller than Uranus.
You got your framing off center there a little bit, so. There you go.
So it's 2.8 billion miles from the sun. So it's kind of, not only is it hard to find, but it's cold.
Just to put that into perspective, that's 30 times farther from the sun than the Earth.
Yep.
And it looks small, but it's actually quite big.
Yeah.
And if you notice, it has kind of a bluish green color. That's caused by methane in the atmosphere. The atmosphere is mostly hydrogen, but it has a lot of nitrogen and a lot of methane. And I see a couple of moons.
Oh, excellent. Look at that.
Yeah, Triton and what's the other one? I forget the name of the other one.
Let me find out the names.
Yeah.
Well, they've got, Neptune has like 13 or 14 moons. So Triton is the one that's farther.
It's Ariel, I think it is.
It could be. It's probably Ariel.
Yeah.
Because that's the second brightest one.
Yeah, I think that's Ariel that we're seeing.
Is that right?
Yeah, the conditions are pretty poor for that.
It's not. No. It's not Ariel. That's the wrong one. It's the four largest moons of Neptune are Naiad, Thalassa, Despina, Galatia, and Larissa, and then Proteus.
So which one are we looking at?
So we're looking at. I'm going to have to use my astronomy software for that.
Yeah.
Hold on. Let me find it.
Yeah, actually, I'm not seeing those moons. Triton, I don't believe that's Triton. At least nothing. The astronomy software I have, it doesn't show anything near the planet. That close.
I wonder if it's just background star then.
Well, it could be. There is a background star that's off to the left. So we may be.
Now, what you can't see, in fact, this was a surprise until we sent spacecraft by it. We didn't realize this, but Neptune has rings. They're just not nearly as prominent as Saturn's rings, but it does have a ring.
You want to try focus on that, Gerald?
I can give it a shot.
Yeah.
I'm not sure I'm going to make it any better.
Yeah, I'm not having any luck on moon information.
Are you in live view?
No,
yes. You're not. You should. Okay, now you are.
I'm in live view.
Yeah, now that I messed it all up. That tightened it up, overshot here. It's hard to do this with your slow shutter speed there. Okay, I think that's about as good as it's going to get. So.
Okay.
Yeah, but that is a really honest color that we're seeing.
Yeah.
From this camera. That's what I love about this camera.
Let me lower the ISO down a little more. It's going to make it a little dimmer, but it'll give it a little more dynamic range.
Yeah. Great. So for most of our viewers tonight, that's the fourth planet you've seen tonight. Don't forget Earth. For some of our viewers who only saw 3 planets, I'd be very interested in knowing where you are.
and why can't you see Earth?
That's right. Let's see if anybody's got some questions here on YouTube. I'm going back to John is chiming in. So, and yes, I'm talking about John Curry. He
What?
thinks we're seeing Triton and a star, and I agree. I think that's true.
All right. I'll take your word for it, John.
All right.
You promised you were going to check in and let your kids have fun on the thing
That's right.
here.
Yeah,
So-
I thought John had the night off. So John,
yeah.
thanks for
What's
checking
going
in.
on here?
Well, his grandkids probably went to bed at 9:30, and now it's 9:50. So Gerald, somebody asked 20 years ago today, what were you all up to?
A 6'1".
Yeah. Well, no, it was. Yeah, that was a rough day. So it is 9/11.
Yeah,
I think they were referring to the memorial.
I was actually working from home that day, and I had just gotten out of bed, and I have a clock radio next to my bed, and they were talking about this plane hitting the tower, and that was before the second plane. And so I turned on the TV just in time to see the second plane hit the tower. So, yeah.
Yeah, I was on the phone. I was on a satellite phone calling ship captains all over the world to let them know what had happened because they weren't getting any live news, and to be careful when they were pulling into port because no one knew what the heck was going on.
Yeah.
It was a very, very surreal morning.
And a lot of those ships have foreign crews, and
yeah, it was a very surreal morning, and I recall similar to Gerald seeing an instant replay of the first plane going into the tower and watching live the second plane, and then going into work later as everybody was streaming out of San Francisco. But I had a job where I had to be there, and it would happen to be on the 15th floor of a high rise, and that was kind of an alarming day, knowing that one of those aircraft was actually destined for San Francisco. But that's another story. But I think everybody knows where they were, what they were doing 20 years ago today.
It's hard to forget. Well, thank you for asking anyway.
Yeah. You know, the next
very relevant question for today.
Yeah. The next day, you know, of course, after that happened, they grounded all aircraft across the entire country.
Right.
The next day I went for a walk, and it was amazing how much quieter it was without airplanes in the sky. I mean, you never think about it when you're out walking around, but there's always this faint din of aircraft flying around in the sky. And that day, it was just super quiet because there were no aircraft in the sky. It was very strange.
Yeah.
So anyway.
So Gerald, do you have any other objects lined up for tonight?
I don't know. What else should we?
I was thinking if we're coming to the end here, why don't we end with the Ring Nebula? Because it's
it's a great idea. Yeah, let's do it.
All right. Well,
okay.
That's going to be a hop, skip, and a jump here. So I'll start hopping and skipping and jumping.
Okay, now I've zoomed out, so you can't yell at me anymore. I'm a sensitive guy.
Oh, we can yell at you still. That's not going to stop us.
You sound like my daughter when she was a kid. Why are you yelling at me? You know, the number of times I actually yelled at my daughter, you could probably count on one hand. But every time I spoke with her in a stern voice, why are you yelling at me? You know? Okay, are we in live mode? No.
Oh no, let's do that. Okay, here we are.
See, we can yell at you for that. You know.
Yeah, it's okay. Oh.
All right, so there's a star.
Okay, thank gosh. I was hoping that wasn't the Ring Nebula. Then I knew we'd have some real problems.
I didn't want to do that. Hang on for just a second. Let me get that back to where it's supposed to be.
Right. You want a cursor? There we go.
No, but I'll take a target.
Bullseye.
Bullseye.
All right, that's good enough for government work here. All right, let's see. Where are we going from here? We're going to the ring, right?
That's
Yes.
correct.
Yeah, we got a ways to go yet. Didn't realize how far over we are. All right, going to another waypoint. Probably a yellow star that we're going to see now.
Yep.
Oh,
Yeah, there it is. Yeah, all right. Let me go west, young man. Oops. All right, sync on that, and now we can go to the ring. Here we go. And you're not going to see this in live mode, I don't think. And we're there. So maybe a 10-second exposure.
Probably even a little more than that, but let's give it a shot.
So the Ring Nebula is what we call a
There we go.
planetary nebula.
this is
Planetary nebulas are the remnants of dying stars.
So let's try to focus. Let me just find a star. You can go to,
You're going to have to do it in live mode then.
all right, so I'm clicking live view. There it is. Okay, there's a star. Can you want to try that, Gerald, or
I can't see it very well.
okay.
Yeah.
All right, let me use the controller.
That's a little sharper.
There we go.
All right.
I'd say that's probably about
Oh,
it.
that's much
Yeah.
better.
Yeah,
That is
yeah,
much, much better.
Yeah.
All right.
Okay, so let's turn that off, turn that off. So we'll pull a 10-second exposure. So it should be coming up right about now. And that's
There it is.
Yeah, okay.
All right. So there's the Ring Nebula. The
Very nice.
remnant of a dying star, 2,300 light years away. This star was once similar in size to our sun, but when it got old, it swelled up, became a red giant. And red giant stars can be 100 times the original size of the star. When they're that big, their gravitational hold on their outer layers is not very strong. And you get some pretty strong internal winds inside the star. And that actually starts blowing the outer layers of the star out into space. And that goes on for thousands of years. And as that happens, it blows away the mass of the star, and you actually lose about half of the mass of the star. And that exposes the hotter interior of the star. And at the same time, the fusion process, which is the driving force at the core of the star, that eventually stops. And so you don't no longer have fusion to produce outward pressure. So all you're left with is gravity to produce inward pressure. What's left of the star collapses into a white dwarf. And white dwarf becomes very, very dense, very, very hot, produces a lot of ultraviolet radiation. And the ultraviolet radiation goes out and hits all that gas that was being blown off while it was a red giant, and ionizes the gas or excites the atoms in the gas and causes it to glow. So we're seeing the glowing ring of gas, looks like a ring, around the white dwarf, which is that little faint dot in the center.
There are some interesting discoveries regarding white dwarf stars in general this week, and there in some studies of globular clusters, it was found that there are populations of white dwarf stars that are capable of being brighter than what was expected, and that's because they still manage to retain a hydrogen envelope around their region of space, and are able to engage in further nuclear fusion, that much more so than your typical white dwarf star would. And this seems to be true in some of the larger globular clusters. So it may be because there's more hydrogen in general in those clusters left over from, their early formation, or some other aspect of being in a globular cluster that creates these conditions.
All right.
Anyway.
Well, I think that's about time to wrap it up. It's 10 after 10.
Well, that was fun.
Yeah.
Saw some
We
good
appreciate everybody chiming in with the questions. And we want to remind you once again that the Chabot Space and Science Center is still closed to the public, although we are doing rental events. And we will be reopening in November. And once we reopen, of course, we will have new exhibits to see, new demonstrations, a new paint job inside the facility. The interior of the entrance area has been reconfigured. Lots of new things to see. So we want to invite you all starting in late November to come up and visit us. But in the meantime, since we're not open to the public, we don't have a lot of revenue coming in. So your donations really help keep us going, not only to, help with the construction costs and so on for refurbishing the interior, but also help paying for the staff that it takes to produce all of this virtual content that you're watching now, plus all the virtual content we have at other times during the week, and our programs with the local schools. We're doing a lot of work with local schools. So we encourage you to click on that donate button. If you're on Facebook, you'll see it at the top. I think it's at the top of the comment section. If you're on YouTube, you can go to the Chabot Space and Science Center website. The URL is chabotspace.org. And if you go there, you'll see a donate button at the top of the page, and click on that and help us out. All right.
All right. Thanks, Gerald.
Okay.
Well,
thanks, Rick.
Everybody have a good
Thanks,
evening.
guys.
And we'll do this same time a week from now, when we'll include the moon in our nightly tour.
All right.
All right. Can't wait for that.
See you guys
Good
next
night,
week.
everybody.
Good night, everybody.
For those of you in California, don't forget to vote.
Some of us already have.